All right, hey folks, welcome back. Hope everybody's doing well. And the last time we got together, we were balancing chemical equations using stoichiometry, putting those coefficients in the front to make sure that we had the same number of atoms on both sides of the equation. Today what we're going to do is we're going to combine the stoichiometry, the balancing of the chemical equations, with some stuff that we've done previously. And previously we made conversions from grams into moles and moles into grams. So we're just going to combine that with our chemical equations. And so today what we're going to do is it's stoichiometric calculations, and we're going to use the mole ratio from our balanced equations. And we'll do a couple of examples on this. And to get us started, we're going to do a chemical equation that's similar to what we did before. This is one of my favorite chemical equations. This is propane. Propane, I love propane. I love getting cylinders of this stuff, setting it out in the backyard and firing up the grill and making carcinoburgers and inviting all of the neighbors over, and it's just a wonderful time. It's something I look forward to every year. Now, the equation for this is C3H8 plus oxygen. Because this is a combustion reaction, we end up producing carbon dioxide and water. Now we have to balance this equation, and on the slide it's balanced, but just as a little bit of a review, you have all of these different elements here. We want to make sure we have the same number on both sides of the equation. What element should we start with? Carbon, yes. Carbon's a good place to start because it only exists in one place on either side of the equation. What element should we not start with? Oxygen, because oxygen appears in multiple places and that makes it much more complicated. Now, I'm going to balance my carbons first. I've got 3 of them here. I've got 1 there, so I'll put a 3 here. That gives me 3 carbons. And then my hydrogens, I have 8 here. So if I put a 4 over here, I have 4 times 2 is 8 hydrogens. And then my oxygens, I have 3 times 2 is 6, plus 4 is 10 oxygens. And so 10 oxygens on this side, if I put a 5 here like that, it should balance out. And you can check my work and make sure, did I do it okay? Or, okay, good, all right, because I make mistakes sometimes. Now it asks us here, how much carbon dioxide would be formed with 10 grams of propane, 10 grams of propane. Now when I do equations like this, what I'd like to do is I like to write down everything that I have as best as I can, just because I can't remember stuff. And so we wrote down the chemical equation, we balanced it, and then we can put in our 10 grams of propane. That's what we're starting with. And we want to find out our number of grams of carbon dioxide over here. So that's what we're given. Here's what we want to find. Now just kind of mentally, the steps that we're going to do is we can't just say, I've got 10 grams of propane, therefore I must have 10 grams of carbon dioxide, because these have different masses and such. So we can't just say that. But what we can do is we can go from grams of our propane here, C3H8, and we can convert it into something else, something that is actually a comparison. So not grams, we'll convert it into moles. So we'll convert it into moles of propane. And once we have moles of propane, we can go from moles of propane to moles of carbon dioxide. And then once we have moles of carbon dioxide, we can convert that into grams. Grams of carbon dioxide. So that's kind of the steps that we're going to take, but we're going to use dimensional analysis. So for dimensional analysis, we'll just start with what we started with here. We have 10 grams of propane. 10 grams of propane. And then I have my next step. So I'm starting out with my 10 grams of propane and I want to convert it into moles. So to convert it into moles, I need to put something here and something there. What goes on the bottom? Grams, excellent, because whatever's up here has to go on the bottom to cancel out. So I'll just put grams here, C3H8, and then I'll put moles up here, C3H8. Now I don't know how many grams there are in a mole of propane, but I could figure this out. I could ask, how would I do that? Don't say Google. Molar mass, okay? Yep, molar mass. How do I find the molar mass? Right, you're giving me the finger, right? The periodic table, okay, yes. Thank you, you're using this, yep, okay, good. So on the periodic table, we look up 3 carbons and 8 hydrogens, add those together, and we come up with some number. And I have here, I did this before class, 44.1 grams of propane. Next step, I'm going to go from moles of propane to moles of carbon dioxide. Now my moles here need to cancel out, so I'm going to put moles of propane. And then I'm going to put my moles of carbon dioxide here. And my ratio is 1 to 3. So every 1 mole of propane, I have 3 moles of carbon dioxide. And then lastly, I can convert my carbon dioxide into grams. And so to get my moles to cancel out, I put moles on the bottom, and then grams on the top. And it just so happens that a carbon and 2 oxygens is 44.01 grams. And that was, I didn't do that on purpose, but the numbers just kind of matched up. It's just kind of dumb luck, the way that worked out. Now, if we did this correctly, our units should cancel out. And so our grams of propane cancel, our moles of propane cancel, moles of carbon dioxide cancel, and we're left with grams. So then, doing the math on this, I ended up with 29.94 grams of carbon dioxide. And so when I made my carcinoburgers in the driveway, I didn't feel too bad because, well, that's just 29 grams, right? That's like that much carbon dioxide, right? I'm not feeling too bad. It's like, okay, you know, climate change, that's somebody else's problem. Okay. Well, now, doing these types of problems, this is a table from your textbook, and it looks kind of complicated. It tells us, oh, we have mass of element, and you multiply or you divide by the molar mass and chemical formulas and such. And you could memorize this. That is an option. It's a lot easier, I think, if we just write out the dimensional analysis and cross our units out. If we do that, we don't have to memorize tables. Now, I was saying I didn't feel too bad about climate change, although my individual footprint on this, but you get a bunch of people together and they start making carcinoburgers out on the grill, you know, lots of them, and some hot dogs and stuff like that, and then, oh, wait a minute, you had to drive to the grocery store, and you don't drive a Tesla because you're a teacher and you don't make that kind of money. So if everybody contributes a little bit, it adds up. And so here is a little bit of information here. 2014, power plants in the United States spewed out 2.2 times 10 to the 11th kilograms of natural gas. How many kilograms of carbon dioxide were released into the atmosphere from all of this? And so, you know, this is a calculation we can do. And we'll start out by balancing our chemical equation. We'll take methane plus oxygen, gives us carbon dioxide and water. So we'll balance that, write that out. First here, methane plus oxygen gives us carbon dioxide. and water. And then balancing it, looks like we've got the same number of carbons on both sides. Our hydrogens, we have 4 here. That's supposed to be a 4. And then to get 4 on this side, I'll put a 2 there. It gives me 2 oxygens, plus 2 is 4, and a 2 there is balanced. And then we're starting out with this stupefyingly large number, 2.2 times 10 to the 11th kilograms. And I have a hard time wrapping my head around this number. Million is 10 to the 6. Billion is 10 to the 9th. Trillion is 10 to the 11th. So this is basically, if I'm doing my math right in my head, 220 billion kilograms of carbon dioxide. It doesn't fit in this. It's a big number. All right. So now, can we use dimensional analysis to convert kilograms into grams and then go through all of this to eventually get our our kilograms of carbon dioxide? I think we can do this. So, take a few moments, write this out, and then see if you can do the calculation. It should be a fairly large number.
A few minutes later.
So the gentleman in the back there, you had the right answer. You had this figured out, right? So can you kind of walk us through what you did, and I'll write it up here as we go along. Now, just don't go too fast because I'm a little slow. All right, so we're going to start out with our 2.2 times 10 to the 11th kilograms. What'd you do? So you convert it to grams, and there's 1,000 grams per kilogram, okay? Okay, you know what I probably should have done is put my units on here as methane. Okay. All right, go ahead. .04 grams of methane per mole of methane. Okay. So 1 mole of methane is 1 mole of carbon dioxide because it's a 1-to-1 ratio, okay? Convert carbon dioxide into grams, okay? .04 grams of carbon dioxide. Convert back to kilograms, and there's 1,000 grams per kilogram. Okay, and this gives us some big number. 6.03 times 10 to the 11th kilograms of carbon dioxide, which is not an insignificant amount. It's a fairly large amount. All right, nicely done. Thank you. Thank you for guiding us through that. So any questions on this? Now, it just so happened on this one, our mole ratio is 1-to-1, and that cancels out. And you're lucky. We're lucky when that happens, but it's not always that way. And this one over here was a 3-to-1. And if we didn't write out a balanced equation, we would have missed this, and we would have been off. So that's why it's important to write our balanced chemical equation. Got to make sure that we take this into account, because it's not always a 1-to-1 ratio.